And then it uses the 0.637, and then it says, okay, multiply it by 0.637, which is the average of an alternation, and then divide it by 2 when it's halfway. And that's what the book is telling us. For me, you can use that. That's fine if that's what you want to use. And I think the formula sheet, I need to get you one of those. The formula sheet gives you both options. It's just that me, I like 2b peak over pi. So I use b peak over pi for half wave, and we're going to use 2b peak over pi for full wave. To me, it works out a lot better. So I don't have to say 0.637 divided by 2 for half wave and 0.637. So now I've got this number I got to float in my head, right? Are you okay? So this is where we're at. So what we're doing now is we're looking at the half-wave rectifier, which they're drawing the AC source, and we're going to go ahead and put the transformer in there. 90% of the time, well, probably even more than that, when you get into a DC power supply, the first thing you're going to hit is the transformer, except with a switching power supply. And we'll talk a little bit about those. We have two categories of regulated power supplies. One of them is called a switching power supply, and one of them is called a linear power supply. And this is in the handout. Linear power supplies are easy to design and they're easy to troubleshoot. And they have the ability to handle real high voltage and real high currents. Switching power supplies are extremely efficient, which means everything can be smaller. So this right here is a switching power supply. Now this guy right here, if it breaks, I throw it away. That's how hard those things are to troubleshoot. And they're hard to design. But they're very efficient. Since they're so efficient, a 20 volt linear power supply would probably be about this big. But if we got a 1,000 volt power supply, it's going to be a linear supply. We can't do that with switches. We'll see that in a moment. So this is where we're at. So what we have is we have three approximations we can use. We have what we call the ideal. So if I use the ideal approximation, I would look at the diode. I would look at the diode like this. I would look at the VI characteristic curve like this. So what I would do with ideal approximation is I would come over here and I would come over here straight line, and then when it got to 0.7 of a volt, I would go straight up. No, I'm sorry, not for ideal. If I did ideal, I can't draw this. This is wrong, guys. Ideal would be if it was forward bias, the diode drops no voltage. So if it was forward bias, so ideal would be here. So as soon as you forward bias it, and reverse bias would go on forever. That would be what we call ideal. Now, when do we use this? Well, the higher the voltage, usually we say around 50 volts, then we don't worry about the 0.7 of a volt, because it's just not enough difference in our calculation between 50 volts peak and 57.3, and 49.3 volts peak. When we get down below 50 volts, then the 0.7 of a volt starts making a difference. So what we do is we use so this is ideal right here. So I started off wrong. So here we say if it's forward bias, it acts like it is a closed switch. If it's reverse bias, it is an open switch. We call this the first approximation. Are you okay? Are you okay? Second approximation, also called the practical mode, shows the barrier potential in the diode model. When the forward bias the diode acts like a switch with a small battery connected in series. When it's reverse bias, it acts like an open switch. And we call this the second approximation. I don't know where these are the figures. So this is what we like to use. So for silicon, we use 0.7 of a volt. For germanium, we use 0.3 of a volt. And if we don't exceed the breakover voltage, we assume it's an open switch. But in real life, it's not, right? You understand that? And then, of course, third approximation would be what the engineers are interested in. And this would be really stuff. This is when you actually figure out the slope. So this is third approximation right here. We take for granted the small current that flows when we first forward bias it, and then we actually use the slope, and then we call this second approximation. I'm sorry, third approximation. We're not going to do that in this class. We're not engineering anything. In fact, you don't even hardly have to use this if you're engineering, because we got so many leeways in this. So normally, if we're below 50 volts, we use second approximation. If we're above 50 volts, we don't take out the 17, because it just don't make no difference, right? Everybody understand that? So I needed to make sure I got through that. Everybody okay on testing the diode? Got any problems there? The book does a poor job on this. If you look at the book, they show using an ohm meter, they show the reverse bias measures 8 ohms. I have never, ever seen a reverse biased ohm meter show 8 ohms. So see where I'm at? What page is that? Where they talk about testing it. So this is figure 5. It's on page 114. They show the thing forward bias. I don't know where this guy got this. So what did I measure? So here they show it measuring 8 ohm. If you use the ohm meter, you'll be able to check it, but if you put it on the ohm meter and it shows infinity or overload in both directions, you need to go up to a next hour scale, right? If it's an auto ranging meter, it'll range until it sees something. But what you're looking for on an ohm meter is you're looking for a really high forward to reverse, forward reverse resistance. You'll never see 8 ohms. What was mine? Mine was, what was it, like 7 meg one direction and 15 megs in the other. So you won't ever see this 8 ohm. But normally we don't use that anyway. We use what? We use the diode scale on our meter. And in that way it shows, and it depends on the meter. What the first thing you need to do when you put it on the diode scale is look and see what your meter shows you when you got your leads open. So when I look at this meter and I put it on the diode scale, look what it shows. So it shows 3.12 volts. So what it's doing is going up to its maximum voltage it'll output, and it's not going to an overload. So this is what this meter would show me for a reverse bias junction. So this meter I like, the other meter I like, so it says overload if it's reverse bias, and it gives us about 7/10 when it's forward bias. But the first thing you need to do when you put it on the diode scale is to see what your meter shows you when you don't have your meter, when you don't have your leads hooked up to you. And this is what it should show you on a reverse bias junction, right? Understand? So this meter will show 3.12 volts for a reverse bias junction, and it'll show if the battery's dead on. So see, I need to replace the battery. It beeps at me, but it checks the meter. And this is a Sperry meter. The other one is a, I don't know what it is. The Sperry meter we've had around for ages. It doesn't even have a category rating on it. So checking with an ohm meter. This is, by the way, on solid state devices or any electronic devices, if you check them in the circuit and they check good, we take for granted they're good. If you check them in the circuit and they check bad, we don't take for granted they're bad. Because there could be something in parallel with them, right? You understand? So if I get, what's the resistance of a transformer? What's the resistance of a transformer? Is it high or is it low? Very low. So I mean, in this circuit, if it's across a transformer, I read that sucker, it's going to read 15 ohms in both directions. And I'll say, okay, the diode's bad, but it's not the diode's bad. It's in series, it's in parallel, or with something that's got a real low resistance in it, right? You don't understand that. So you got to be real careful on that. So even the book, the first thing it starts off with is, so this is the power supply that we're working for. So right now we're going to start off right here. So we're going to hook up these half-wave rectifiers. They work fine. They work great. It's just that we can't use them in a lot of applications. Then we're going to move over to what? We're going to move over to this guy, and we came in and add some additional components. So here's our rectifier. And then what we're going to do is we're going to add a filter to it. And notice what we get right here. We don't see it anymore. So my rectifier is going to give me this, but once I add the filter, I get this right there. Now you can see it's not pretty DC, but it is DC now because it never goes to ground, right? And then what are we going to do? The last thing we're going to do in power supplies is we're going to look at regulators. So what's regulators going to do for us? Well, they're going to take that unregulated DC and generate a regulated output. Now, in power supplies, when we mean what regulation means, it means the regulator, it maintains a almost constant DC output to the load with varying loads and varying input current, varying input voltage. As long as you stay within the specifications of the power supply. So every power supply says, well, I can regulate if the input voltage is 120 volts plus or minus 10% and my output load current is not over 10 amps. And if you exceed 10 amps, the thing don't regulate anymore, right? Or if you drop it below 10% of the input voltage, it don't regulate anymore. If you get it 10% above, it'll probably burn up. So the first regulators we'll look at is the Zener diode. It's a regulator. And then later on, we'll get into integrated circuits. Like that thing I dropped on the floor a while ago. That's an integrated circuit. It's been ran over. But this guy right here is a voltage regulator. It's 3 leads too, by the way. They're hard to see. Well, they're not hard to see. So notice the case is completely metal. So this right here is one of your conductors. So this is the regulator. So one of the leads will put unregulated voltage. The other lead will be connected to common or something, and then the output is going to be regulated voltage. This is an integrated circuit. And what's an integrated circuit, guys? Well, multiple. It contains an entire circuit on a single wafer. So this is nice. It looks like a transistor, but it's not. It's an LM323. I think this is the variable regulator. So that's what we're working toward on our power supply. And we're going to do it one step at a time. We'll start off with a half-wave unfiltered power supply, and then we'll throw a filter into it, and then later on we'll throw a regulator into it. This is the math that comes up and gives us the 0.637, by the way. I thought that would be interesting. So here they deal with a little bit of calculus. They deal with integration, which is not easy to use. So you can do this if you want to. Or we can use what? You can use 0.3637 if you want to. I like to use this guy right here. To me, it's just easier to learn. 2dp code 5. I'll pull that off the internet somewhere. I'll about the average of an alternation. So that's the one we like to use right there. Now, you can use these if you want to, but you got to figure out the delta theta, the 1 over the integer of between 0, integrating between 0 and pi. So this is what a halfway rectifier consists of. It consists of an AC voltage source. How many diodes? 1. And a load. If the diode's anode is pointing toward the source, when the input voltage goes positive, the diode forward biases and conducts. So if we point the anode toward the source, and this is where you determine the polarity. Don't worry about figuring out current flow. If the anode points toward the source, it's a positive supply. If the cathode points toward the source, it's a negative supply. Does it change the math? No. The math is the same. It's just that your final answer, if it's a negative supply, you put a minus out there. If it's a positive supply, you just leave it off. And this is what it says. With the diode's anode pointing toward the source, then what we end up with is a positive supply. So if the cathode points toward the source, we get what? We get a negative supply. If the anode points toward the source, we get a positive supply. You can figure out all the current flows if you want to, but it makes it real easy. So this is what we just got through. So what happens to the this is the positive supply. How do I know this is a positive supply? Just by looking at it. Because the anode of the diode is pointing toward the source. And what does it do with the negative supply? Well, the negative supply is dropped across the diode because the diode is off. So if I had the ability with a scope to look across the diode when it was forward biased, I would see about 0.7 of a volt, but that would be it. So it'd be up just a little bit. This is what I would see with an oscilloscope. On the negative alternation, we'd see the entire voltage across the diode because it's an open switch. An open element in a series circuit drops the entire voltage. Over here, I would see this, right? You understand? This is going to be 0.7 of a volt less than what's over here because of the what? Because of the diode. And what would I see during the negative alternation? Well, the negative alternation, I would see 0. Because all the voltage is being dropped across the what? The diode. Now, of course, to us, the voltage source is going to be a transformer. We're not going to deal with 120 volts. We're going to use transformer. In fact, we'll use the transformer that's on the trainer. The transformer on the trainer is one of these guys. And I can't draw it exactly. Let me add one more. You know what we call that? Oops. This is what's on the power pole out in your house that powers your house. We call this a center tap transformer. And ours is a 12.6 volt center tap transformer. So if I go between the tap and the center, we get 6.3 volts. If I go between here and here, I get 6.3 volts. If I go across the whole thing, I get 12.6. Close to it. We refer to this as a center tap transformer. This is what's on your house. So your house, if you go around off the two outsides, you get 240. If you go between in the center tap, you get 120. And that's what's out on your house, the center tap transformer. This is what's on the trainer. We'll show you all the transformer. All you got on the trainer. The trainer comes up here and just labels the 6.3. It don't label the 12.6. So if you look at the trainer, it's up at the top. So this is the transformer we'll use in our lab. So we're not going to use more than 12.6 volts. So the trainer kind of doesn't do a good job at labeling it. Let me bring the camera back up. So here's the transformer as soon as it focuses in on the trainer. Right here. So it shows the 0 as being what? Center being is 0. So what would happen if I use my meter and measure from here to here, I measure 6.3. If I measure from here to here, I get 6.3. But if I go from here to here, I get what? 12.6. Don't understand that. And we don't say it's a 6.3 volt center tap transformer. The way we nomenclature it is across the outside. So we go out and we buy a 12.6 volt center tap transformer. So that transformer up on your post is a 240 volt center tap transformer, right? Don't understand that. So the trainer doesn't do a real good job. These are regulated power supplies, by the way. And what we'll do before long is we'll strip this thing apart and we'll look at these circuits inside this actual trainer that does it. And of course, first thing we got is a multi-winding transformer. One set of windings is this guy right here. We'll get to see the actual power supplies in this trainer. We might even split this thing up and look at the power supplies. We're not going to take my scope apart, even if you want to. So the power source would be the transformer. Here we could use either a 6.3 or we could use a 12.6. I don't know what it's asking for. So how do we solve it for this thing? First thing I need to know is I need to know this voltage right here. And then we solve for VP. And what's VP equal to? VRMS divided by 0.707. That's the process, right? Then what do I do next? Well, next I solve for V peak out. So V peak out is going to be equal to V peak out rich, is going to be equal to V peak minus VF. VF is what we call the forward voltage drop of the diode. For silicon, we're going to use 0.7 of a volt. And that's all, that's what we're using. Every diode we have for rectifiers is germanium. We'll show y'all some germanium diode, silicon. We got germanium diodes, we just don't use them in the lab. And then what do? Then my volts DC would be equal to V peak out divided by pi. Very, very, to me it's something. You, I know it's new. Or it could be divided by 1/2 of 6.637, whichever one you want to use. By the way, in this class, we don't require you to show your work. But it's optional for you to show your work. The problem is that if you miss this, you're going to miss that, you're going to miss that. If you don't show your work, I'm not going to try to figure out how you got your wrong answer. But if you solve for this wrong, and then you take that wrong answer and put it right there, and you take this wrong answer and put it right there, you miss that one right there. You don't miss the other two. You don't understand that. It's up to you if you show your work. And we have students that don't do it. Sometimes they get by with it, sometimes they don't. Sometimes everybody that does it exactly right. But if I start grading and this is wrong, and then you took that wrong answer and put it in there, I'm not going to go out there and figure out what you do. I'm not going to redo your math for you. What am I going to do? I'm going to count that wrong, and I'm going to count that wrong. I'm not going to figure out how you got your wrong answer. Now, if you don't do the math right, then it's going to be wrong anyway. But showing your work in this class is optional. It's up to you. A lot of people don't want to do that because they got to write stuff down. They do their math in their calculator, and then they don't want to turn around and write that down. And what's nice about that is that sometimes you can see where you made a mistake just by writing the math down, right? You say, oh, I forgot to do that. You know? I forgot to take out that 0.7. The average value of a half-wave rectifier, the value that you would measure across using your DC voltmeter. And this is what a resistive load will see. A resistive load will do that work. It does not do V peak. It does not do V peak to peak. It doesn't do RMS. It does this DC average. It's DC, both DC. Of course, here they're showing 3.18. So now, if you use 6.37, you got to remember 3.18 for half wave and 6.37 for full wave. If you're doing 2V peak over pi, you just drop the 2 for half wave and you leave the 2 in there for full wave. So you can see right off the bat, full wave is going to give us twice the voltage, but it's going to cost more money, right? So this is why we get that average right here. We get that DC average now, but it's this averaged with this, right? It's averaged with the whole cycle. This is the cycle. So that means if I'm putting 60 hertz into the thing, then my pulsating DC is going to be at 60 hertz. And what is a cycle? It's one repetition, right? And this is a repetitive waveform. What did I do with my trainer? I gotta find my wire. I've got some right here, but I don't. Oh, this class is almost over. What would this class gets over 9 o'clock? It's a full term class. What we'll do next class is we'll wire these suckers, we'll wire this thing up, and we'll look at it with an oscilloscope, calculate it, then we'll put a meter across it. We'll see how close our calculations come to that measure. You will be surprised. Pretty close. Especially if we measure. So what we're going to do, we're going to use 120 volts. That's what National Electric calls the optimal or the nominal voltage. We're going to do our calculations with 120 volts. Odds are they're not going to be exactly 120, so we're going to do the calculations without making any measures. And then see how close we get. You guys okay? So what chapter are we working in? We're going to do half wave, then we're going to do full wave center tap, and then we're going to do full wave grid. Learn how to calculate it. Like everything else, you might not ever use math, but you'll have a really good understanding of the way these things work. And by the time you get out of here, you should be able to design yourself a linear power regulator. That's nice to have. You want to do stuff like this. Alright guys. See y'all Thursday. What y'all need to bring in? We're going to do a lab Thursday. We're going to do the characteristics curve, right? Make it bigger and make it take that. And the lab book. Bring your lab book, I'm sorry. Your lab book. Where'd you get your lab book at? DC, it's the same lab book. You sold it, you're screwed. The DC instructor should have told you not to sell your lab book. Lock that door down for me over there, okay? Don't know how to do it? Lock that door over there for me, okay? Don't know how to do it? Yeah. I think Greg does. I think he's done it for me before.